As a child, I enjoyed playing a team-based word association game with my friends. 4 players were divided into 2 teams. One player would whisper a secret word to an opponent, who must then say a related word aloud to help their teammate guess the original whispered word. The teammate gets 1 guess. If incorrect, the next team can describe the secret word with 1 word. The first to guess the original whispered word wins. For instance, if I hear banana, I might say yellow to my teammate. But yellow can be associated with many things, including taxis, sunflowers, lemons, or gold. So while there's a possibility that my teammate might guess banana from the word yellow, it's not the most likely outcome. Using the word peel could improve accuracy, since peel is more often associated with the word banana than yellow. There are many yellow things, but peel is frequently linked with banana. Perhaps there are even better associations than peel, right? Anyway, to be good at this game, you must think of the word that maximizes the likelihood of your teammate guessing correctly. Some words may be too complicated, so you'll need a few tries to understand them, providing more context. If I'm given grapefruit, I might need 2 turns. First, citrus, which gives my partner a low success chance. Then, bitter, which ensures they guess correctly. Alternatively, saying citrus and pink also offers a high chance of success. Context is crucial. So why am I telling you this story? This is a great analogy of how language models operate. A language model primarily predicts the optimal word to fill a blank space. For example, if a user types to be or not to be, that is the model would respond question. Like in the word association game, the model fills in the blank with the next most probable word. So language models are probabilistic, capable of predicting the missing word in a sentence based on the context provided by preceding words. We generally have 2 types of language models: masked and autoregressive. Masked language models can guess the missing word regardless of its position in a sentence. So, for example, consider the sentence water, blank space, at 0 degrees Celsius. In this case, the model could use the information before and after the blank space to fill in the missing word, freezes. Autoregressive models predict the next word. They'll use the context of preceding words and guess what should follow. An autoregressive model will be able to forecast that the next word in water freezes at 0 degrees is Celsius. OpenAI's GPT models are autoregressive, which work by conditioning each prediction on all previously generated words. But how can language models predict the next word in a sequence? This is rooted in statistical learning from vast amounts of data. A language model gains the ability to work with language by analyzing and learning from the patterns and structures found in the input text it processes. This involves digesting large datasets containing diverse linguistic styles and uses, which enable the model to recognize and predict likely word sequences in different contexts. Over time, the model builds a probabilistic map of word associations and dependencies, enhancing its ability to generate coherent and contextually appropriate responses to more complicated prompts. The outputs of language models are open-ended, meaning that they can use the vocabulary built by learning from training data to generate an infinite number of possible outputs. The word generate is key, hence the name generative AI. Initially, AI developers focused on creating models tailored to a single language, but modern models are capable of processing and understanding multiple languages. Generally, we discuss language models, though often the focus is on large ones. Obviously, the difference between the two is size. But what size qualifies a language model as large? The term LLM lacks a formal definition and can be used quite flexibly. The term large language model reflects their training on vast data quantities, and this data volume continues to expand over time. So what is deemed large today will not be in a few years. For example, GPT-3 was trained on 175 billion parameters, GPT-4 over 1 trillion, and GPT-5 is likely to use even more. It's believed that the richer the training data for LLMs, the smarter and more versatile they become. In our next lesson, we'll talk about the process of training LLMs and why it's scalable compared to what we had before. Thanks for watching.